Okay, in this next video, we're going to derive the Boltzmann distribution, which is a fundamental, probably the most fundamental piece of statistical thermodynamics. And before we do that, I want to remind you of something that we saw back in chapter 3, which is that as the number of molecules gets larger, there's a growing spike in probability, so that one macro state is so much more common, meaning it has a higher multiplicity than all the others, that the system will always be found in that macro state. So if you look back to pages 35 and 36 of these notes, I went through this calculation for 6. This is when we were doing quantum harmonic oscillators in solids, in 2 solids that were in contact. So we had 6 quantum oscillators, so you can think of that as we had 6 molecules or 6 atoms. And in that case, the most probable configuration had 100 different, the multiplicity was 100, and the least probable was 28. Okay, so about a factor of 4 difference. Now, if we take the number of oscillators and bump it up to 500, and I went through this calculation back on these pages as well, then your maximum most likely point is here at the peak, where the multiplicity is 10 to the power of 114. Whereas down here at the bottom of the peak, the multiplicity is 10 to the power 81. So now we went from a factor of 4 to a factor of 10 to the 33. 33 orders of magnitude more likely to be found here than here. And that's with only 500 particles. And so this one I didn't calculate, but just to illustrate the point, if n is greater than 1,000, this peak is going to get even taller and even thinner. And so this is the idea here, is that as the number of molecules grows, the most likely state becomes so likely that it is effectively the only macro state that you will ever find that system in. Okay, so now I'd like to talk about how can we go about finding where this peak is. In other words, finding out what is the configuration, this macro state, that is going to be the most common and effectively the only macro state that we'll find the system in. So how do we find this? Well, as usual, we're going to take the derivative, set it equal to 0, because this is a maximum, and see what we find. So we'll be taking the derivative of w, that's the function whose maximum we want to find. And w is a function that equals a function of n0, n1, n2, and so on. So these are all the variables that w depends on. We can see this clearly if we look back at our definition of the multiplicity for a configuration like this. It's n factorial over all these other factorials, where capital N is just the sum of n0, n1, and n2. So really the only independent variables that we have are n0, n1, n2, and so on. Okay, so w is a function of those variables. So I'm going to remind you of the definition of a differential that we were using extensively earlier in the semester. So if I have a function of 2 variables x, y, then what is the differential of that function equal to? And remember, it's the partial derivative of the function with respect to x times the differential of x plus df dy dx. Okay, so remember we were using this a lot earlier this semester. This is for a function of 2 variables. We have, I don't know how many variables here, potentially 10, maybe hundreds. Okay, so we need to write this in a more compact form that incorporates all of these terms, because you see what's happening is for each variable that the function depends on, we're taking the partial with respect to that variable and multiplying by the differential. And we do that for each of the variables that it depends on. So a more general case would look something like this for dw. If I want to know the differential of w, then I'm going to have a sum, right? This is a sum. Now, this one only has 2 terms. This one's going to have n terms, or some number of terms. And each element of the sum is going to be the partial derivative of w. with respect to, I'm going to number these with I. I'm going to index them with I. So with respect to Ni times dNi. Okay, so this is the same formula as this, but it's more general because it covers potentially lots and lots of independent variables. Okay, but earlier we were talking about taking the natural log of W because it's useful. We can use Stirling's approximation among other reasons. So let's do that. So instead of looking at the differential of W, let's look at the differential of the natural log of W. And the formula doesn't change much. All I do is replace W with natural log of W. And this is an important equation that's going to come up again. Let me call this equation 1. So we want to find a solution to equation 1 if we set it equal to 0, okay? Because there we have found the peak of the natural log of W. If we can find where this equals 0. Okay, so that's going to be our goal. But there's a couple of constraints that we have to incorporate. So we have 2 constraints that we need to be concerned with. The first one is that we want to require each possible configuration, which remember that's the macro state. So we want each macro state to have the same energy, which we'll call capital E. Okay, so we only want to consider macro states that have energy equal to capital E. And to write that mathematically, that's to say that the total energy is going to equal the sum of the energy of each state times the number of molecules in that state. Okay, so this sum needs to add up to E for whichever macro state we consider. Okay, and we're varying Ni up here to find the maximum. So if I take the differential of this, then I have the differential of a sum, which is the sum of differentials. This is a constant, so it's not changing. So the differential of this equation looks like this. Okay, so, and we want, and the differential of a constant is 0. Okay, so we want this to be true. So I'm going to call this equation 2. This is our first constraint. Our second constraint is on the number of molecules. We want each configuration to have the same number of molecules, which we call N. All right, so writing that, N is equal to just the definition that we saw before, the sum of all the Ni's. And once again, if I take the differential of the left-hand side is 0. The differential of the right-hand side, the differential of a sum is the sum of differentials. Okay, and so we need this to be true in order for the number of molecules to be the same in each macro state. We need this to be true in order for each macro state to have the same energy. All right, so I'm going to call this equation 3. And so what we want to do next is we need to solve equation 1, but subject it to these constraints, 2 and 3. So we want to solve 1 subject to the constraints 2 and 3. And you may have seen this technique before, but a common and very powerful way of solving a max-min problem, which is what equation 1 is, when we have constraints, is the method of Lagrange multipliers. So you may have seen this method before, Lagrange multipliers. if you took a Calculus 3 class, that's when I first saw it, was in Calc 3. So if you took a Calc 3 class, you almost certainly saw the method of Lagrange multipliers. Okay, so we're going to use that now in order to solve one subject to these two constraints. Okay, so the method of Lagrange multipliers is that we take each constraint and we multiply it by a constant, which is called the Lagrange multiplier. And then we add those constraints to the original equation and solve the combined equation. So in this case, we're going to call our constants alpha and negative beta. And this negative sign is chosen because it'll be useful later. But it's up to us to choose these constants however we like. I'm free to put a negative sign in front of it and assume that, you know, maybe b is already a negative number, and then I end up with a positive number. It doesn't really matter. So we're going to use the minus sign because it'll be useful in a minute. And so now I want to solve the original equation that I was trying to solve, which was this sum of the derivative of the natural log of w with respect to ni, dni over I. Okay, I was trying to solve that equal to 0. But I'm going to add to this my constraints. So constraint 1, the first constraint, which I actually called equation 2, was this. Actually, let me add this one first. I'm going to add this one first. Okay, so I'm going to multiply this one by alpha. So it'll be alpha times this sum that I'm adding to the original equation. And then I'm going to subtract beta times my other constraint right here. And we're setting this equal to 0. And now this is what we want to solve. And notice you can see the reason why we took the differentials of our constraints earlier, is now every term includes a sum over d and I. So I'm going to combine all of these sums. So I have the sum of this times d and I plus, this is all inside the sum of alpha times d and I minus beta times energy of state I, all of this times d and I, and that's all inside the sum. Okay, so I took these three sums, I combined them into one sum, and I factored out the d and I. Now, one way to solve this equation is if I have a sum and it's equal to 0, an obvious way to solve this equation is to say that this is 0 for all I. So every term in the sum is 0. So that's a solution to this equation. So let's see what happens if we use that solution. Okay, so here's a solution. I want this term in parentheses, which is this, to equal 0 for all I. I don't know if you've seen the symbol before, the inverted A. Inverted capital A means for all. So I want this to be true for all I. Now, let's go back to the formula that we found for the natural log of the multiplicity earlier. So here it is, a few pages back. I'm going to call this equation star. And so now I'm going to substitute star into this, okay? And actually, I'm just going to substitute it into this first term because that's the only term that has the natural log of w. So then I have this term is equal to the derivative with respect to ni of the natural log of w, which is n natural log n minus sum of ni natural log ni. And I just realized back here in this equation that I started, I forgot to put the natural log in front of w. Okay, so this is the equation for the natural log of w that I substituted right here into this derivative. Okay. Now we need to take the derivative of both of these terms. So here I've distributed this derivative to the two terms, And now let me call this term number 1. I'll call this one number 2. And we're going to take a look at each of them separately. So number 1, I'm taking the derivative of a product. So I need to use the product rule. So I get the derivative of n with respect to ni times the natural log of n plus n times the derivative of ln of n, the natural log of n, which is 1 over n. This is a derivative of natural log. And then chain rule, I have to take the derivative of the argument with respect to ni. Okay, so here I have n over n, and that cancels. And something else to notice about this is n is n naught plus n1 plus n2. So the derivative of n with respect to ni well, that's a derivative of each of these. And here we assume that all of these variables are independent, meaning that n1 does not depend on n naught. They're all independent. n2 does not depend on n1 or n naught, and so on. So each of these derivatives is going to be 0, except for the one where the numerator is the same as the denominator. And that's only going to be true for one value of I. And in that case, let's say it was I equals 1. Let's say I over here equals 1. Then dn0, dn1 is 0. I'll do another term just for purposes of the example. The derivative of n2 with respect to n1 is 0. The derivative of n1 with respect to n1, that's 1. So all the terms are going to be 0 except for one of them, and that term will be 1. Okay, so this then is just 1. And so this simplifies quite a bit. I'm left with the natural log of n plus, and this simplifies to 1. Okay, natural log of n plus 1. That's going to go here. All right, let's take a look at term number 2. So term number 2 is right here. And the first thing I'm going to do is I'm going to take, this is the derivative of a sum, which is equal to the sum of derivatives. So I'm going to take this derivative into the sum. That's going to be my first action. Okay, so it looks like something like this. And I need to be careful here because this sum is using a subscript I, but that doesn't necessarily have to be the same as this subscript I, because this I represents which variable we're taking the derivative with respect to, whereas this I is the one that's controlling the sum here. So what I'm going to do is I'm going to change the i's for the sum into j's. Okay, I'm going to change that i's into j's for this this is like a dummy variable, right? It goes away after the sum is calculated. So it's just for the purposes of this shorthand notation, whereas this I is determined by the left-hand side of our equation, is where we get the value of I. Okay, so once again, I have the derivative of a product, so I have to use the product rule. So I'm going to get the sum of the derivative of the first, which is the derivative of nj with respect to ni, times ln nj, plus nj times the derivative of the second. So that's going to be the derivative of ln nj is going to be 1 over nj. And then chain rule, I need to take the derivative of what's inside of the natural log. All right, so we see that these nj's cancel. Now let's look at these derivatives. The derivative of nj with respect to ni. What does that equal? again, the variables are all independent, okay? So if I and j are unequal, then that's like the derivative of n1 with respect to n naught, or the derivative of n3 with respect to n1. As long as I and j are different, then we're going to get 0. So this derivative is equal to 0 if I is not equal to j. However, if I does equal j, then I have the same variable in the numerator and the denominator, and so that derivative simplifies to 1. And so that's if I equals j. So this derivative is either 0 or 1, depending on the relationship between I and j. And you may have seen this before. This is called the Kronecker delta, okay, which is basically just shorthand for this behavior. It's equal to 1 if I equals j, and it's equal to 0 otherwise. So now I'm going to put my Kronecker delta in up here for these. And I have the sum over j of delta ij ln and j plus delta ij. All right, and I factored out the delta. And so now I have the sum over j, and every term has a delta ij in it. What does that mean? Well, that means that delta ij is going to be 0 for every term in this sum. It's going to be 0 except for the one term in the sum where I equals j, in which case it equals 1. So I hope that you can see that without writing it out, but without me writing it out. If you want to write it out, feel free. But what's going to happen to this sum is it's going to reduce to a single term. The only term that's left, the only non-zero term remaining, will be the one where I equals j, because all the others are 0. So if the only term remaining is the one where I equals j, then that term looks like ln of ni plus 1, the thing in parentheses where I've replaced j with I. And this is often how Kronecker deltas manifest themselves. Inside of a sum, they basically have the effect of picking off one term of the sum, and you replace the j with I. Okay, so this is term number 2. So now let's take number 1 and number 2 and put them back into our previous equation. Okay, so just to remind you what we started with the derivative of the natural log of w, and then we substituted our equation for the natural log of the multiplicity, and we ended up with this, where we had term number 1, I called it number 1, minus term number 2. Okay, so let's put that together. So here's my derivative of the natural log of the multiplicity. That's equal to term minus 1 minus term minus 2. So number 1 came out to be ln n plus 1. So I have ln n plus 1. And I'm going to subtract from that term 2, which is ln ni plus 1. And you can see that the 1's cancel because I have 1 minus 1. And then I have natural log of n minus natural log of ni, which we can combine into the natural log of n over ni. So we got this nice simple result after all of that math. And to remind you of how we went off on that tangent, we were trying to calculate this term because we had a solution to our max-min problem with constraints, which was that this plus alpha minus beta epsilon I must equal 0 for all I. Okay, so we have found a simplified way of expressing this, which is the natural log of n over ni. So we're going to put that back in to this equation. So let me call this equation, I don't know, solution. All right, so we're going to plug this into solution. And we get that the natural log of n over ni plus alpha minus beta epsilon I equals 0 for all I. Okay, so I took this result, plugged it back into the equation I called solution, and we end up with this. All right, now I'm going to solve this for n over ni. So actually, I'm going to solve it for Ni over N. So the first thing I'm going to do is I'm going to take the reciprocal of this, which I have to offset by putting a -1 superscript, which I can pull outside. So this is equal to the natural log of Ni over N. And that's equal to the negative alpha minus beta epsilon I. So I just subtracted these two terms over here. You see the minus signs cancel. And now I exponentiate both sides. And I get that Ni over N is equal to E to the alpha minus beta EI, epsilon I. And I can rearrange this and solve for Ni. So Ni is going to be N E to the alpha minus beta epsilon I. And then notice that N, remember, is defined to be the sum of all the Ni's. And here's a formula for the Ni's. So I want to plug that in right here. This is going to go right here. And I end up with the sum of N e to the alpha minus beta EI. N is a constant that I can pull out, and it's going to cancel with this N. So what I'm left with is 1 equals the sum of e to the alpha minus beta epsilon I. And notice that alpha also does not depend on I. N didn't depend on I, so I can pull it out. Alpha doesn't depend on I, so I can pull it out too. And I get, so basically every term in the sum is multiplied by e to the alpha. And now I'm going to solve this for e to the alpha. And I'm going to get 1 over this. And now I'm going to take this, I'm going to put it back into this equation here that I solved for Ni over N. Because now I have an expression for e to the alpha. E to the alpha is 1 over this sum. Okay, so I'm going to put that back in here. Let me call this equation star star, because I think I already have a star. All right, so we're going to plug this into star star. And we get Ni over N is equal to e to the minus beta epsilon I over the sum. And this is it. At last, we have arrived at the Boltzmann distribution. I'm going to change this index to a J like I did before, since this is a dummy index for the sum only, leaving the I up here to match with the I have on the left-hand side. All right, so this, after all of that work, lengthy derivation, this is the Boltzmann distribution. Probably, unarguably, the most important equation in statistical thermodynamics. Now, it's proven later that beta, which was, remember, one of our Lagrange multipliers, it's proven in section 13F that beta is equal to 1 over KT. Okay, so that's proven in section 13F. I'm not sure we're going to get that far. We probably won't. All right, so why all that work? What does this tell us? So what this tells us is, remember that Ni is the number of molecules that have energy EI, okay? So Ni is equal to the number of molecules with energy EI, epsilon I. And N is the total number of molecules. So this is the ratio of molecules that have EI over the total number of molecules. So this is the fraction of the molecules that have energy EI. And so this effectively is giving us this fraction, which turns out to be the probability that the system is in a macro state. I'm sorry. Yeah, that the system will be in a macro state with energy epsilon I. Okay, we'll talk more about probability in the next section. And this quantity in the denominator here is often, so this is the sum of all of these exponentials for all the different possible energies, all the different energy states. And whereas on the numerator, it's just this exponential for the one energy state that we're interested in, which is state I. Okay, so this number on the bottom doesn't change unless the system's energy states change. And so it's given a special name. So the denominator is called the partition function. And it's often given a letter. When I first learned it, we used the letter Z. Your book uses like a script Q. So the partition function Q is just the sum of e to the minus beta epsilon j. And so then Boltzmann's distribution can be written that this probability is equal to e to the minus beta epsilon I over q. Okay, so the last thing I'd like to do is talk about the relative population of Ni versus Nj. So in a way, we're going to use the Boltzmann distribution to answer the question, which is more likely that we would find a molecule in state I or a molecule in state J. And we're going to do that just by computing the ratio Ni over Nj, where we plug in the Boltzmann distribution for each one. I'll use this form right here. So Ni is equal to n times this. So on the numerator here, I have n times this over q. And I'm dividing by nj. Well, nj is this equation with I replaced with j. Okay, so I'm dividing by, so I'm going to take the reciprocal of this. So it's n times e to the minus beta epsilon j with the q on top. So the script q. And the q's cancel, and so do the n's. So I end up with e to the minus beta epsilon I minus epsilon j. Okay, so this is effectively just another expression of the Boltzmann distribution. And actually, this version is the one that's probably more commonly used than the first one. So a lot of times you'll see the Boltzmann distribution written in this form. And remember, beta is equal to 1 over kT. So the temperature appears in this. And this is giving us the ratio of the populations of state I versus state J. So we can use this to figure out which population, or I'm sorry, which state is going to have the larger and which the smaller population. An interesting special case is the case of absolute zero. So as t approaches 0, beta approaches infinity, and e to the minus beta, if beta is approaching infinity, approaches 0. So this ratio approaches 0. And the reasoning here is that all of the molecules are in the ground state. In a way, So whatever you choose for I, the ratio of I and I to, say, the ground state is going to be 0. Okay, so this is a commonly used form of the Boltzmann distribution, and this is where I'm going to wrap up section 13a. And in the next lecture, I'll go on to cover just a few topics here and there that remain in chapter 13, and that'll be it for chapter 13. Okay, so I'll see you in the next lecture.